Assalamualaikum warahmatullahi wabarakatuh, and good day to everyone. So today we are going to discuss the recap problems. Not all of the problems, just a selected one, so that it can hopefully it will refresh your memory. Okay. So I'm going to start with this very basic reading from the tables kind of problem, which is the table for R134A. Okay. So you need your property tables with you in order for you to complete this exercise. All right. So let's have a look at the first one for A. Before we begin, please make sure that you look at the correct section of the property tables. Right now, for this question, we are dealing with R134A. So you should have table A11 ready. Okay, so not ideal gas. Okay, this is refrigerant R134A. So please make sure when you receive a problem, exercise, or in the quiz, in the test, make sure you look at the substance that we are using, right? All right. Okay, so for the first one, um, we are, we are given two information, which is the saturated liquid as well as the temperature. Okay. So from here, I think this is the easiest problem to start with. We know we are given saturated liquid. So meaning that it is located at, so if I draw a small S diagram, okay, it should look something like this. So saturated liquid, it is located over here, okay, on the saturated liquid line. Okay, so let's say we are dealing with H right now. So let's say this is H, F, this is H. Okay, so we know it is HF. So at HF, your X, the quality, it should be 0. Okay, so we know this. And since it is between 0 and 1, so when we are given the temperature, we can know that the P corresponds to the P set. So if we go to temperature negative 24 over here, so I already highlighted temperature here. At negative 24, the corresponding P set is 1111.37 kilopascal. Okay, and because we know that it is saturated liquid, your X is 0, it is located on the line. Hence, to get the H value, you should read your HF at the given temperature, which is negative 24. So your HF over here, is this one, 20.31. Okay, so let's write it down, 20.31. So that's for the first problem. Okay. Excuse me. Right now, for B. Okay. For B, again, this is quite easy to start with because we are given the value of X. X equals to 1, it means the location of our state is here. So if we drag it down, Hg, so it is on the saturated saturated vapor line. So saturated vapor. Okay. All right. So I already have the steps over here. So X equals to 1, so it is saturated vapor. So if we go to the value given, we have P. P equals to 170 kilopascal. Now, I think it is easier for us to read from the pressure table. So if we go to the next table, A12, it is a pressure table, P and T. So if we look here, 170 is between the value of 160 and 180. So meaning that you have to interpolate. All right. So you have to do interpolation. So I already extracted the value. So this is the range that we are looking at. Okay. The value that we want is y. Okay, 170 is given to us. We want y. So we have to find y by using interpolation. So I have the steps over here. Okay. So I'm not going to go into details. You can have a look at the steps. So when you calculate, you interpolate, you're going to get your y, which is correspond to temperature is negative 14.165. Okay. How do you know this is a correct value? Okay. Let's have a look over here from the tables. Your answer, negative 14.165, it should be correspond or it should be located in between the value that you interpolate. So in this case, it is located between 15 and 12. So it makes sense. Okay, so that's how you check your answer. So negative 14, negative 14, oh, sorry, that's the negative 14.65. Okay. How about the H? Right. Again, if we go to the H, let's make it smaller. All right. If we go to H, again, you have to do interpolation because the value is located in between this. Okay. So as you can see over here, I already did the interpolation. So your value is located between, again, this is what was given to us, 170 kilopascal. I'm sorry. 170 was the pressure. Okay. Sorry. This is what we want to find. So this is P and this is H. All right. So if you look over here, P was given to us, yes, 170, that's what the value was. So it is located between 160 and 180, 160 and 180 over here. And the value that we want to interpolate should be located between these two. Because we know it is okay. Okay. All right. Now, if you look over here from the diagram given, from the question given, your X is 1, so we know it is at the saturated vapor. So over here, I make a mistake because I use the HF value. So this is wrong. Okay. All right. So the right calculation should be here, the right interpolation. So we were given 170 in our question, the pressure, and we have to use Hg because we know X equals to 1. Okay. So if you use Hg, so over here, the value in between. So your answer, when you interpolate, you're going to get 242.04. So if you look over here, it is located just in between the upper and the lower value. So which is correct. So for B, you got T and also your H. Okay, so the state is saturated vapor. Okay, so now let's continue with C. So for C, we have to find the temperature and also the X and phase description. H and P was given to us. All right, so how should we proceed? Okay, so if I can just move this. Okay, all right. So for this part, if you look from the tables, at 600 kilopascal, okay, if we go to pressure table at 600 kilopascal, which is over here, okay, at 600 kilopascal, the HF and HG. So let's check our HF and HG over here, this line. Okay. So your HF is 81.50 over here, and your HG is 262. Now, when you check your H given in the problem, your H given was 180. So your H given is in between F and G. So we know then it is between it is in between the graph, which is saturated mixture. So it should be saturated mixture over here. Okay, okay now, so when we know it is in saturated mixture region, so we can use the given pressure to find the T set. Okay, so at 600 kilopascal, your T set is 21.55. So your T is 21.55 Celsius, which correspond to T set over here. Okay, all right. Then how can we find the next information, which is the X, right? So if you remember, you were given this information or this equation in order for you to calculate H or X. So now we want to calculate X, you rearrange the equations, you get the following: H minus HF divided by HFG. And we know all this value, we know H that's given to us. We know HF from the table, 81.50 just now, and your HFG. If HFG is the one in between, 180.95 over here. Okay, so you get 0.544. So that's your X. Now let's go to D. Okay, so for D, now we are given the X 0.6 and the temperature. So since it is 0.6, which is between 0 and 1, we know this is in saturated mixture region. Okay. Now let's look at the other information, -10. Okay. So if you look at here, since it is in saturated region, mixture region, so we can take the value of P which correspond to the T given. So at T -10, so T -10, the corresponding P set is 200.74 kilopascal. So at -10 over here, your corresponding P set is 200.74. So let's write down 200.74 kilopascal. And how about your H? All right. So now to find H, using similar equation to what we have over there to find the X, okay, we know our HF and X and also HFG because we can find, okay, I already highlighted over here, HF is this value, HFG is this value. So substitute, because we know X that was given to us, you get H equals 162.142. Okay? So your X is 162.142. All right. Okay. So next, let's proceed to E. All right. Okay. So for E, um, let's move our table. Okay. Now, for E, we were given the temperature -14 and the corresponding pressure 500. Okay. If you're given these two information, P and T, the easiest way to determine the region or the information of the state is by looking at the temperature. So meaning that we look at the pressure table to compare the T set. Okay? So if you go to the pressure table at P equals to 500, okay, this pressure table. Now, over here, at P 500 kilopascal, the corresponding T set is 15.71 Celsius, which is higher than the given. So the given to us was -14. So what does this mean? Because the given temperature is lower, means that it is in the compressed liquid region. Okay? If the temperature given is higher than the T set, it means it is in the superheated region. But right now, because the T set is higher than the given, so we are in the compressed liquid. Excuse me. Okay. When we are in a compressed liquid, the value of X is none. It's not available. Because remember, your X is only applicable between the middle region. So if we go back to this diagram, this plot is now, see here, your X only valid in between this. So this is X equals to 0, X equals to 1. Okay. If it is located between superheated region, in the superheated region, the value is none. Okay. There's no X value. Okay. So there's no X value for compressed liquid. Okay, how can we get the information of H? All right. Excuse me. Now, for compressed liquid region, to get the value is by looking at the H, which can be estimated to be close to the value of HF, saturated liquid line, at the given temperature, which is negative 14. So you read the value of H for the compressed liquid region, the value of H can be estimated to be close to the value of HF at the given temperature, negative 14, which in this case, if we go back to negative 14 over here, so your corresponding HF is this 33.23, or is it 33.28? 28, okay, this value. Okay, all right, so this is 33.28. Okay, so remember for compressed liquid region, your HF can be estimated, okay, can be estimated to be close to the HF at the saturated temperature of the given temperature. Okay, let's move to F. For F, you were given pressure, the 1200 kilopascal, and the H. So how can we proceed from here? Now, so if we look at our value of at given pressure, P equals to 1200. Okay. At 1200 kilopascal over here, the H, the corresponding H, 300.63, the given H for us. Okay, if we look at the H over here, track the lines. Now, so at 1200 kilopascal, the given H was 300.63 kilojoule per kilogram, which, if you look over here, when compared to this is HF, this is HG, which is higher than the HG given, which is 273.92. So what does it mean? Because the H is higher than the G over here, the HG, means it is in superheated region. Okay. So again, remember why this happened, because we have H, this is temperature, we have the lines. If this is HF, this is HG. So anything larger than HG means that it is located on the superheated region. Okay, so in this case, we know it is in superheated vapor. Superheated vapor. And when in superheated vapor, we know there is no X. The value of X is negligible. Okay, now, how can we find the value of temperature, which correspond to 1600? Because this is no longer valid. Okay, remember, this is for the saturated table. So now we know that we are in the superheated region. We have to use this superheated table. Okay, so we have to use superheated table of the refrigerant 134A. Now, please be careful, because in the superheated table, we are dealing with megapascal. So right now we are we were given in terms of kilopascal, 1200 kilopascal. So if you convert 1200 kilopascal, you will get 1.2 megapascal. So you have to go into the correct parts of the table, okay, which is here, 1.2 megapascal. Okay. So 1.2 megapascal, and we were given H. Okay. So from this table, find the H. Okay. Remember, this is the H column. Okay. Between this and this, which value correspond to the given H. So in this case, we are lucky because the value is straight away given directly from the table. So 300.63 is here, and the corresponding T is 70 degrees. If your value is not it's not given directly from the table, meaning that you have to interpolate. If the value is in between the values, then you have to interpolate. So in this case, you can straight away take the value of temperature, which is 70. So you get 70 degrees over here. Okay. So last one. For G, we know we were given the value of X. So we know this is in terms of saturated vapor. Okay. So if we go to temperature at 44 degrees Celsius, 44 degrees, okay, over here, the corresponding pressure is 1130.7. So you can write this down, 1130.7, and H. So since it is saturated vapor, so your H should be Hg. So it should be this value, 273. 273. Okay. So that is roughly the exercise to refresh your memory. So to recap, basically be careful of the substance given in the problem. In this case, we are dealing with 1348. But for other type of gases, for example, air, which we commonly use, it's just the same procedure to be follow on. Okay, so just be careful on the terminology. So make sure you understand what is X, for example, when we have to use it, how to find it. Okay, so that's the important parts that you need to remember. Okay, so now let's have a look at one other problems to conclude this recap session. Okay, so this is the problem that I would like to highlight. So you were given helium, which is to be compressed from 105 kilopascal and 295 Kelvin to 700 kilopascal and 460 Kelvin. You were given heat loss, 15 kilojoule per kilogram, and then you can neglect the kinetic energy changes. You were also given the mass flow rate of 60 kilogram per minute. Okay. So basically what we are looking at right now, we want to find the power input, okay, which is the W in over here. All right. So the way I like it, when you were given any engineering problem, especially for thermodynamics, this is the steps that I would like to follow. First, you start with what was given. So in this case, we are quite lucky because the diagram basically already summarizes everything. So usually, some of the diagrams were not given or incomplete. So you have to put all the information from the sentences into the diagram to help you visualize better. So in this case, I just to redraw it again because everything was given. So we were given Q out, 15 kilojoule per kilogram, P2, T2 that's given, as well as P1 and T1. We were also given the mass flow rate. Okay, remember, mass flow rate. So means we have m dot over here, okay, in terms of uh, time per minute. Now the question asks the value or what is the output, the int, W in of the compressor. Okay. So before we start, I think that's it's better for us to list down some of the assumptions to be made, okay, so that we can simplify the problem. First, it is steady flow. Okay, so steady flow means there is no change over time. Okay, it's zero, right? then we can neglect the kinetic and potential energy because the question already listed the assumptions. Okay, so we can neglect Ke and Pe. Next, be careful because we are dealing with helium. Okay, always be careful of the substance. So you can assume helium to be an ideal gas. Okay, most of the time when we deal with thermodynamics problem, we assume it to be ideal gas. Okay, or um, basically make the assumptions to simplify our calculations. Okay, so ideal gas, that's our assumptions with constant specific heat. Okay, so let's look at the steps. Okay, so the solution. So we start with the energy conservation equation. Start with E in minus E out. Now, because we have dot, okay, means that we are dealing with time. Okay, so that's why we have dot over here. E in dot, E out dot. Okay, we know that it is steady state or steady flow. So change of energy over time can be neglected. So cross out. So and then remember, next we get E in equals to E out. Okay, in terms of mass, in terms of time. Okay. So remember, the whole energy conservation starts with this. Okay? When we are dealing with flow, we have mass flow rate, yes, and we have H. Instead of U, we have H because U plus PV. U is the internal energy, PV is the fluid energy, or the moving fluid energy. So we have H plus KE and PE. And in this case, because the KE and PE can be neglected, so we cross this out. So what we are left with is the energy of W in, that's what we want to find, plus MH, M dot H1, KE and PE already cross out. So for out, we have Q out, the heat loss that's given in the problem, and also we have MH2. So this is the first step that you need to do right. If you got this wrong, the whole calculations at the bottom will be wrong as well. Okay. Now, if you rearrange, you get W in minus Q out equals to MH2 MH1. All right. If you notice, when we're dealing with ideal gas, okay, we also most of the time will need to use the specific heat, the constant specific heat. Okay? Or we can use CP or CV. So if you remember, CV when we deal with H, CV when we deal with U. Okay, now, since we have MH2 minus H1, it is H, so we can have MCP T2 minus T1. So we substitute. Basically, this is constant specific heat problem. So from here, we get MCP T2 minus T1, okay, because we're dealing with H. All right. So now we know we want to find W in. Q out was given to us. M was also given to us. CP. Okay, CP. Basic. Okay, oh, sorry, down here. Okay, this is what we want to find. Q out was given. M was also given. MCP, you can get this value from table A to A, okay, which correspond to this value, 5.1926 kilojoule per kilogram from the table. Okay. T2 and T1 was also given to us. Okay, all right. So from here, if you substitute this, Q out was 15 kilojoule per kilogram. Okay, but remember, we are dealing with rate, okay, over time. Okay, something that is flowing over time rate. So means you have to convert from here 15 kilojoule per kilogram into something that is in rate, so that you can cross out, because over here, if you have apple, excuse me, if you have apple on the left, you also need to have apple on the right, so that you can combine apple with apples to get two apples. But if you get, let's say this is orange on the right side, so you have to convert orange to get apple. Okay, so what this means is you have to convert everything in terms of rate. Okay. So how can we do that? We were given 15 kilojoule per kilogram. Okay, and remember, this is in terms of per kilogram. If you multiply that with the mass flow rate given, mass flow rate is in terms of mass per second. So mass flow rate is 60 kilogram per minute, and we convert from minute to second. So 1 minute is 60 seconds. So you're going to cross this out, kilogram, kilogram, cross out minute with minutes, and you are left with kilojoule per second. Okay. So the next one, for MCV, you do the same. M, 60 kilogram per minute, you convert into second. So you divide it by 60 seconds, cross this out. Okay. You multiply by CP, which is from table A to A, 5.1926. And you multiply by the temperature, which is this is T2, this is T1. So make sure the units are consistent. Kilogram, cross out, minute, you cross out, kilojoule, then Kelvin with Kelvin. So if you did not write down the units, most of the time you will get it wrong. Okay. For example, over here on the first part here, if you did not write down the unit, most of the students will not multiply by the mass flow rate. Then you will have kilojoule per kilogram plus kilojoule per second, which is not a consistent unit. Okay, it's not valid. Okay, so from here, you move down, you get 872 kilojoule per second, which is equivalent to 872 kilowatt, because joule per second is equal to watt. Okay, right. So the important take-up from this exercise is the importance of units. Okay. Units, unit conversion. Okay. Excuse me. And also the specific heat. Okay, when to use the specific heat constant. Sorry, the specific heat equation. Okay, CP or CV. All right. So I think that's all I have for the recap problem. Thank you, students. See you in the class.